to the, what are we doing? We did 3 minus 1. And then enter, let's see. Ooh, why is it thinking so much? I broke it already? What? Am I connected to the internet? It did it before class without any issues. Let me change this to a 2, right? Because that's really what it is. I don't think that's going to do anything. There, okay. See the answer there? The answer is 2. Okay, which matches with what we thought, right? Now, what if we wanted to know what 1 factorial was? Then we would do gamma of 2, which would be our integral would change to what? This would be integral 0 to infinity. We plug in 2 right here, 2 minus 1, 1. So we get t e to the negative t dt. Understand? Integration by parts once this time. And if we do that, let me go back up here and change this to a 1. We get 1. Make sense? Okay, now, what if we wanted to know what 0 factorial was? That would be gamma of what? 1. Okay, what's gamma of 1? Integral 0 to infinity. If I plug 1 in here, this is the cool one. If I plug 1 in here, what do you get? 1 minus 1 is 0, right? T to the 0 is 1. So all you get is e to the negative t. Right? And if you do that, I'm just going to get rid of that. Oh, no, I'm not. Guess what we're going to get? One. We get 1. We get 1. And that's why 0 factorial is 1. Because gamma of 2, the reason 0 factorial is 1 is because gamma of 1 is 1. Now, the great thing about gamma is now you can actually do fractions. So remember this? We didn't know what it was. But we could do it here. It would be integral 0 to infinity t to the, plug in 1/2 right here. 1/2 take away 1? Negative 1/2. And then e to the negative t dt. And if I try that, I need to do right here t raised to the, nope, whoa, what happened? It all died. T raised to the negative 1/2 times e raised to the negative t. There we go. And we are going to get, now remember, improper integrals, sometimes they converge, sometimes they diverge, right? So let's see if this one converges. It converges, look at it. Holy shit, square root of pi. Whoa, wasn't expecting that. Okay, but that's the answer, square root of pi. So imagine I could continue doing this, right? I could continue doing gamma, plugging all these different values into gamma, and that means gamma has a graph, doesn't it? There's a graph for gamma. And here's the graph of gamma. It's in red. You see that? And what hopefully you can see there is that, I know that that's hard to see, but what you can see that if I do gamma of 3, right? Gamma of 3, it's this red point here. Gamma of 3 is 2, right? Gamma of 3 is 2. But gamma of 3 is what factorial? 2 factorial, right? So all these dots here, the red dots, are your gamma, and then the blue dots are the factorial. So we know 3 factorial is 6, right? And then notice that I don't have gamma for 4. Let me do gamma for 4. There. Oh, shit, went too far. There. Gamma of 4 is 6, right? And that's 3 factorial. But see, gamma has, you can define gamma, here you can have gamma defined for fractions, things in between, right? And even better, you can actually plug in negative numbers into gamma. You can plug negative values. And when you plug negative values into gamma, you get the whole graph. And so you have gamma. Gamma has places where it's undefined, so you have vertical asymptotes. But, or not vertical asymptotes, yeah, vertical, you call them vertical asymptotes. But that's the graph of gamma. All right? So factorial, right? 5 times 4 times 3 times 2 times 1. Factorial is actually just the gamma function, but restricted kind of only to the non-negative. Yes?
For the fractions, how does it know where to stop?
What do you mean stop?
Because you stopped at 1.
No, so you can't, when you want to plug a fraction in for a factorial, you can't. You have to think of it as gamma. You can't, this formula only works when you have non-negative integers. But, right, but gamma will give you the same answers as this, but gamma can handle fractions and it can handle negative numbers as well. Right, so I'm not telling you that you can do 1/2 factorial this way. I'm telling you that you can do 1/2 factorial using gamma. All right, so hopefully that settles it. We can move on. Sorry. I just wanted y'all to see why 0 factorial is 1. All right? Okay, so a special property of factorial, something that, again, we're going to use. The notes online say, you know, that this is only good for like non-negative integers, but are you looking for gamma? Gamma's not in there. Yeah, gamma's not. I don't think gamma's even in our textbook. Yeah, I haven't looked for it, but all right. So this special property, n plus 1 factorial over n factorial. All right. What is this? Well, let's start with the easier part. We know the bottom, right, is just n times n minus 1 times n minus 2, ... until we get down to 1, right? That's the definition. That's the definition of n factorial, right? You start with n, you take 1 away, take 2 away, take 3 away until you get to 1. n plus 1 factorial, where do you start? You don't start at n, you start where? N plus 1. So you start with n plus 1, then you take n plus 1 and subtract 1. So what's n plus 1, take away 1? Well, we'll see what that is. Then we do the n plus 1 and take away how many? 2. And then we do the same thing until we get down to 1, right? But what is this piece right here? What's that? N, what's this? N minus 1. And then the next one would be what? N minus 2. And do you see that that cancels with that, that cancels with that, that cancels with that? Everything cancels, and all you're left with is what? The n plus 1 that was in the very front. Who has a question on that concept? Because I'm going to give you another one. All right? How about this? What's n plus 1 factorial over n plus 3 factorial? Which one of those is bigger? N plus 3 factorial or n plus 1 factorial? The denominator is bigger, isn't it? N plus 3 factorial, because n plus 3 is bigger than n plus 1. So this number is bigger than that, and we're going to do factorial. So that should be a bigger answer on the bottom, right? So I'm going to start with the bigger one. N plus 3 factorial is, what's the first thing? N plus 3. What's the next piece? N plus 3, take away 1, which would really be n plus 2. And then take 1 away again, n plus 1. Now watch this right here. N plus 1, what's going to be next? N plus 1, then n minus 1, then n minus 2, all the way I get down to 1, right? But notice the n plus 1 and all that shit that comes next, right? Isn't that the numerator? Isn't that what the numerator is? Yes? So what I'm going to do is I'm going to stop right here, and I'm going to put in different colors so you can really see it. This n plus 1, instead of writing it all out again, I'm going to put the factorial right behind it. And that right there is basically me saying I'm stopping here because I know the rest of it expands out, right? But that matches up with the numerator, n plus 1 factorial, and then what can I do with those? Cancel them out. And then that would leave me, careful, with what on top? 1, right? And on the bottom, n plus 3 times n plus 2. Okay. That's just to show you how we can work with these factorials. I feel like maybe one more is in order. Just one more. What is 5n plus 2 factorial over 5n minus 1 factorial turn into? All right, which one is bigger, 5n plus 2 or 5n minus 1? 5n plus 2, so I'm going to start up there. Okay, let's start writing out 5n plus 2 factorial. So it starts at 5n plus 2, and then what do I do for the next one? Subtract 1 from that. What's 5n plus 2 take away 1? 5n plus 1, right? And now, take away again. What happens when I subtract 1 from that? 5n. When am I going to stop doing this? I mean, because I could go all the way to 1, couldn't I? But I'm going to stop when I see the denominator happen, which is the next step, isn't it? The next step is 5n minus 1. And then I could keep going, right? I could keep going. But I noticed that if I just throw the factorial onto this piece right here, right, that this, the rest of the way, is the denominator. And I can get rid of them. And so my answer is just those three factors right here. All right, good? All right, that's factorial, special properties, continuing in my notes here. So sequences, right? We have this definition. We started last class with this idea of a sequence. I told you a sequence is a function that is restricted to the natural numbers, right? You can only plug in 1, 2, 3, 4, 5, so on and so forth. Okay, that's what a sequence is. Visually, though, what is a sequence? So let's take a look at that. So I'd like for us to compare two different things here. I'm going to give you, first of all, a function, f of x equals x squared, versus the sequence a sub n equals n squared. What is the difference between these two? Well, if I were to draw like an x-axis, y-axis, and I were to graph this, right? We all know that this would be a parabola, right? And it would go like this. It would be continuous, right? Draw it without picking up my pencil. I could plug in any value I want between negative infinity and infinity. That's what it would look like. The sequence, on the other hand, is not a nice continuous curve, is it? The sequence is just some points, right? When I plug in, where do we start here? 1. When I plug in 1, I get 1. So it's that dot right there. When I plug in 2, I get 4. And when I plug in 3, I get 9, right? Over here, 9. So it's just a bunch of dots that live on the function. Like if you were to convert this sequence to a function of x, then the dots on that sequence would live on the curve x squared in this case. All right? So that's what a sequence looks like. And you can see that, of course, domain-wise of this is just 1, 2, 3, 4, 5, 6, so on and so forth. So this right here is a visualization. I have a sequence here that we're going to look at. We're going to look at the visual of this. The sequence is the sequence a sub n equals -1 to the n, and then times n squared. So -1 to the n is going to create an alternating sequence starting with negatives, and then it's going to be squaring. And I listed out the first few terms, or the first few numbers of the sequence, right? Let's see it visually. That's what it looks like. What happens when you plug in 1? When you plug in 1 to this, you get -1. Plug in 2, you get +4. Plug in 3, you get -9. Plug in 4, you get +16. So what's happening is it's like, you know, negative, positive, negative, positive, negative, positive, and this is parabolic. It looks, the shape kind of looks parabolic, but you're getting parabola like upward and downward because you're flipping back and forth, all right? But that's the sequence, visually. All right, now this is something where I can put in any sequence I want. I can type it in. So I've typed in this sequence for us to look at. A sub n equals, I did n squared over 1 plus n squared. I just made one up, all right? Now let's take a look at it. We'll start with the first 5 points here. You know what, let me reevaluate this. There they are. All right. What happens when I plug, we're only looking at the first 5. What happens when I plug in 1? Let's see. 1 squared? 1. So what's the first term of this sequence? 1 over 1 plus 1. This is 1/2, right? So y'all see there at 1, we're at 1/2? Yeah? What's a sub 2? What's the second number in this sequence? So 2 squared, 4 over 1 plus 4. This is 4/5. Do you see at 2, we're up there at 4/5? We'll do one more. At 3, we're at 9 over 1 plus 9, which is 9/10. Do y'all see a pattern here? The denominator is always one more than the numerator, right? But the numerators are all the perfect squares, aren't they? 1, that's 2 squared, 3 squared. So the next one would be 4 squared over 17. Next one would be 5 squared over 26. Next one would be 6 squared, 36 over 37. Do you all notice that these numbers are never getting bigger than 1, right? Never bigger than 1, but they're getting closer and closer to 1. And we can see that if I show you more numbers. Watch, let's do the first 50 of these. There's the first 50 of them, okay? Okay, there's 1. So you can see they're getting closer and closer. Make these a little smaller. How about we look at the first 500 of them? There they are. What does it look like is happening there? What would you call that? Like, it seems like our sequence is, our sequence as we're moving to the right, our sequence looks like it's going like headed towards something, never getting there, right? Like an asymptote almost, right? We call that convergence of a sequence, all right? Look at the sequence we did before, this one. As we move to the right, what happens to the sequence? Like this, right? That's divergence. They're not going to something in particular. It's kind of jumping back and forth, isn't it? They're jumping and getting further away, as opposed to the second one I showed you where they all seem to be headed towards the same thing. They want to get closer to 1, right? So that's what's next. The limit of a sequence, right? Just like we had limits of a function, right? Didn't we have functions in Cal 1 and we said, hey, what's the limit of a function? What's the function doing as you go to infinity? Same exact concept here. We're going to ask, what's the limit of a sequence as you go to infinity? So that's our next definition. So given a sequence, a sub n, we will say the sequence has a limit of L if, when we take the limit as n goes to infinity, the sequence goes to L. All right? So when you talk about sequences and limits, we are always letting n go to infinity. In Cal 1, when we were doing limits in the beginning of class in Cal 1, we would do the limit like, hey, what's the limit as x approaches 1? Or what's the limit as x approaches 0? With sequences, we're always going to infinity and seeing where's the sequence headed. Now, if that limit exists, because we know from Cal 1 not all limits exist, if the limit exists, the answer is L, then instead of writing this whole notation, we will just write this. A sub n with an arrow to L, and that lets you know that the limit is L. We will also say, in this case, that A sub n converges to L. All right? So we got to take some limits. We're going to be doing limits again. Now, if the limit does not exist, if it doesn't exist, or, this is a big or when we take the limit we get positive or negative infinity, then we will simply say the sequence diverges. So divergence of a sequence is one of two things. Either the limit doesn't exist, or it's going to a positive or a negative infinity. In either case, that's divergence. All right? All right, we just visualized it a second ago, but I guess I've got more for you. So here's convergence. Here's that idea of convergence. See, the sequence as we went out to infinity, it looked like our sequence was headed towards 1, right? There's like this horizontal asymptote where it's headed towards 1. As opposed to divergence, sorry, this is another example of convergence. Ooh, this one's interesting. Look at this convergence. Do y'all see that this sequence kind of oscillates, right? But the oscillations get smaller and smaller. So our limit here is 0. Even though we go above and below 0, keep going above and below, we're funneling in towards 0. Meaning that the absolute value, the distance from our number to 0 keeps getting smaller as I go down. So this would be a convergent sequence. That's convergent. Do y'all see that converges to 0? Here's something that diverges. Is that obvious that that diverges? What is it doing? It's going 1, but then negative 1. And then 1, and then negative 1. You can't say that converges. To converge, you have to go to a single number. This is like 2 different numbers, right? That would be divergence. Yeah, okay. We're just going to keep going. So now our first theorem in this section. All right, this theorem says that, let me just simplify this theorem with the picture, with what I have on the board here. That theorem says whatever that does as x goes to infinity, that does as n goes to infinity. Does that seem reasonable to you? Like, whatever the red function does, the dots have to follow along because the dots live on the curve, don't they? So that theorem says, all right, if you're ever trying to find the limit of a sequence, then you can convert it to a function of x first, figure out that limit using Cal 1, and then whatever that limit is your answer here. All right? Now that's an important theorem because of what? Why is that important? I don't want to get too far ahead. We are about to start having to take limits, right? And this theorem is saying that to do this, we're going to look at the function instead of the sequence. That's important because in Cal 1, when we were doing limits, we got this very powerful thing towards the end of limits. What was it? The rule? That's for derivatives, for limits. L'Hopital, right? L'Hopital comes in and like saves us, right? What do you do to do L'Hopital? You get 0 over 0 or infinity over infinity, and then you do what? Take the derivative. The derivative of a function, right? The derivative function relies on the continuity of the function. Your function has to be smooth and continuous for us to differentiate it. Dots are not smooth and continuous. You can't take, what's the derivative of a dot? You know what I'm saying? Like, there's no tangent line on a dot because you don't have that curve to kind of fit your tangent line in. Do you all understand? There's no slope at a dot. So in order to get around that, what we say is, okay, if we ever are doing this and we run into a situation where we might need L'Hopital or something like that, it's okay, because we'll just switch it over to a function of x. Whatever that answer is, that's also the same. But you have to apply the theorem. You can't start taking derivatives of this because it's not a function. It's a sequence. Okay, so that's just the visualization of that. You have, in red here, can you all see here? You have a red curve. That's f of x. Whatever that curve does, the black dots do it as well, right? So if the original function, if the limit goes to 0, then so does the sequence. And now we have our first example. It's kind of a rough example. Let's not do that one first. Let's not do that one first. Let's do this one. Let's do the one that we had on the board just a second ago, right there. Okay? Let's take this one. Let's take the limit as n goes to infinity of n squared over 1 plus n squared. Now look, I'm fair warning here. Everything you learned about limits in Cal 1 is back. Okay? It's back. So all that stuff that you did is going to resurface in this section. L'Hopital. All right, so here we go. I'm going to let n go to infinity. Let's just check what happens real quick. If I let n go to infinity, n squared is going to be infinite, right? 1 plus n squared is still infinite, so we have infinity over infinity. That's perfect for L'Hopital, right? I can bring in L'Hopital's rule. However, I can't do derivatives of this. So the first thing I'm going to do is I'm going to convert this over to a limit as x goes to infinity of x squared over 1 plus x squared. That's using the theorem that I just put on the board that we're going to look at what the function does. Whatever the function does, the sequence does. And now I can use L'Hopital. So I bring in L'Hopital's rule because I have infinity over infinity. There's L'Hopital. I'm letting you know I'm doing it. And now I take the derivative of the top, which is 2x, derivative of the bottom, which is also 2x, and 2x over 2x is 1. And so our answer is 1. Right? Our answer is 1. So I can conclude. Therefore, 3 dots in the shape of a triangle means therefore. Okay, make a little note of that. That means therefore from here on out. Therefore, the limit, no, let me do it this way. I'll use different notation. Therefore, I can conclude that n squared over 1 plus n squared goes to 1. See, that's the new notation. This means the limit of it goes to 1. This notation means that that equals 1. This sequence heads to 1 as n gets big. Now, I'll be honest with you. As we move through this section, I'm going to stop doing this. Okay? Because it takes up too much time to switch it to x and then come back and say this. Okay? I am going to do L'Hopital's on this later, but it's just to save time. And I'm not there yet. All right? So let's go to that example right there. Sine n over n squared. This will be a good test to see how you learned limits back in Cal 1. Okay, so I want the limit as n goes to infinity of sine n over n squared. All right, so let's talk about what happens as n goes to infinity here. What does the sine function do as you go to infinity? Go to infinity on the sine function. What does it do? Goes up and down. Now, these are dots, right? So dots along that oscillation. Is that headed to a single place? No. So actually, that limit does not exist. On the top, the limit doesn't exist. The bottom is headed where, though? Infinity. L'Hopital only works if you have infinity over infinity or 0 over 0. This is not the case, right? We have does not exist over infinity, right? However, depending again on your Cal 1 experience, what I can say is that the numerator is bounded. Okay, bounded. This is a bounded function on top. Sine is always between -1 and 1, right? So if you have something on top that's bounded over something that becomes infinitely big, guaranteed this goes where? 0. As long as your numerator is bounded and your denominator grows, what's going to happen is it's going to squash down to nothing eventually. Now that's something in my Cal 1 class, I teach that, say anytime we see bounded over infinity, it goes to 0. So your background on this might be a little different, just letting you know. Bounded over infinity goes to 0. And this doesn't even have to be positive, it can be negative infinity as well. All right, so the answer is 0. All right, next thing. Here's the picture of it. Here's the picture of sine n over n squared. It's like it's trying to be a sine function, but you're dividing it by bigger numbers. So what happens is it kind of squashes that sine function down, and it just kind of gets smaller and smaller, like a smaller amplitude as you go on, and eventually tapering off to nothing. All right, squeeze theorem. We're not going to use this. It's the same one from Cal 1, though. Yeah, I'm not going to do that. Okay, new theorem. All right. This theorem says exactly what it says. If the absolute value of a sequence goes to 0, then the sequence goes to 0. If the absolute value of a sequence goes to 0, then the sequence itself goes to 0. Right? The arrow, again, the arrow means that when you take the limit, you get 0. That's the theorem. Look at that example. Find the limit as n goes to infinity of -1 to the n over n squared. Limit n goes to infinity, -1 to the n over n squared. All right. So I'm going to use this theorem. There's actually another way you could do this one. Because look at the top. What can you tell me about the top? As n gets bigger, it's just going to what? Switch, right? 1, -1, 1, -1, and 1, -1. And what's the bottom do? Goes to infinity, right? So that's this, isn't it? Because the top is either 1 or -1. 1 or -1. 1 or that's bounded, right? And then the bottom gets huge. So you could just say 0 right now. But what I'm going to do is I'm going to use the theorem. So this right here, this is the a sub n, right? I want to know what happens to it. So I'm going to use the theorem, and I'm going to look at the absolute value